So we have two things that we're going to do today. The first thing, as you can guess, we're going to look at U substitution and how a definite integral will impact that process. And then we're also going to look at something called average value. Okay. So let's go ahead and write down this example right here. It looks very similar to our example, I think, number 1 from your warm-up. It's just to the 5th power instead of the 50th power, okay? And we have 1 to 3 as our limits of integration, okay? So there are two ways you can go about doing a U substitution with a definite integral, okay? First, let's just do the U substitution, okay? When you have a problem where you have a composition and something left over to where U substitution works, go ahead and go through the U substitution process and kind of forget about your limits of integration. So in this case, we can let U equal x squared plus 1, which means du is 2x dx. Okay? Just like we did in our warm-up, we have that 2x dx, so we can replace that with du. So this becomes the integral u to the 5th du. And for right now, I am just going to leave off those limits of integration. I'm just going to forget about them for a moment. Okay. Well, what is the antiderivative of u to the 5th? 1/6 u to the 6th. Okay. So now what we can do is we can say, all right, well, I have my antiderivative. Let's go ahead and change it back to x's like we would normally. But now we're going to evaluate from 1 to 3. So when we go back to x's, we can bring back our limits of integration so that we can use the fundamental theorem of calculus. Okay? Now we can say 1/6, 3 squared plus 1 to the 6th, minus 1/6, 1 squared plus 1. I might go ahead and let somebody help me out by punching that into a calculator, unless you can do it off the top of your head. That would be fine. 10 to the 6 is, what would you say? Okay. Minus 2 to the 6th.
2 to the 6th.
Okay. And then, so 1 million minus 64 divided by 6. Okay. Run status. Did you get that? Did you get that? You just gave up?
Well, yeah, once you said that, we stopped.
Okay, how about everybody math 9 that integral to make sure that Brindley got to the right place, because Brem gave up. He didn't. I do trust you. Brem really trusts you. Math 9. Punch that in. Max, you remember the order which you have to do everything?
It's like x squared plus 1.
Yeah, comma x, comma 1, comma 3. Yeah. Good? All right. Make sure you can get to 166,656. Caret 5, like caret 5. So what do you need to do? Okay, now we're going to do the same problem. So rewrite it, because now I'm going to go a different way with what we do with our limits of integration and our use. Okay? And then you can decide which method works best for you. Okay, so just like before, we are still going to let u equal x squared plus 1. We are still going to let du equal 2x dx. So now this is going to become the integral, like before, of u to the 5th du. But now what we are going to do is we're going to change our limits of integration to u so that we don't have to go back to x's ever again. Okay? So if x is 1, punch that into here. What would u equal when x is 1? 2. So now my limit of integration is 2. Okay. When x is 3, we punch that into here. What would u equal? Those numbers are sounding familiar, right? From before. So now what we have is 1/6 u to the 6th evaluated from 2 to 10. So 1/6 10 to the 6th minus 1/6 2 to the 6th, or 666,500. 600. What this does is it saves you the step of going back to x's, but it adds in the step of figuring out what these values are right here. Okay? No matter what, you're going to need the 2 and 10. Right? Here we just did them ahead of time, whereas here we went back to x's and plugged in our values, and here we saw that 10 and the 2. Okay? So it doesn't matter which way you go about it. Do whatever works best for you. Okay, so kind of think about what method you like. Okay. And we're going to do an example, another example before I turn you loose on an example by yourself, because I want you to remember what happens when we don't have exactly du in our integral. Okay, so go ahead and write this example down. And go ahead and identify what you think u and du should be. Ethan, what do you have for you?
4x cubed plus 1.
Okay. Which means du is 12x squared dx. Okay. So let's just remember, because it's been a couple weeks, we have x squared dx. That 12 is kind of extra. So we need to balance this out. 1 over 12 du is exactly x squared dx. So when we come to rewrite our integral in terms of u, 1/12 du is the same thing as x squared dx. And then we can write u to the fourth inside. How many of you think that you would like to change our limits of the integration right now in terms of u? Okay, how many of you want to just leave them off and go back to x's with the du1 and the 3? Okay, well, not everybody voted and it's about half and half. So I'm going to go through this with changing the u's so just so that you can see it one more time. But if you want to do the other method, then you go on ahead and you should still get to the same answer. Okay? So if our x value is 1, then that would make our u 5. Okay? And if our x value is 3, ooh, you're going to have to help me out. 3 cubed times 4 plus 1. Oh, you guys are way ahead of me, huh? Okay. So we have 1/12 times 1/5 u to the 5th, evaluated from 5 to 109. So we have 1/60th times 109 to the 5th, minus 1/60th times 5. Yes, that's got to be a big number. What do we get? Did anybody put that in their calculator? It's 0.7. Nice. 7. Okay, there it is. Now, as you can imagine, you may need your calculator on some of these calculations. I still want you to be doing the integration by hand. You can check it with Math 9. What does that mean in like a quiz test type situation? I will be very specific what I want to see. Okay, the calculator part of our test, I'm probably going to be okay with you using your calculator Math 9. All right, but like our quiz on Wednesday, if I let you use your calculator, I want to see the integration so you can check it with Math 9, but I need to see all of the work leading up to it, and it all needs to make sense. Do you understand that? Like, your work needs to lead to the answer that you have. Okay. All right. So here's one to do without me. Work together at your pod. Compare your final answers. Pick whichever method you think works best for you. But I want to know what the area under the curve from 0 to 1 of this guy is. Mm-hmm. Right. So, like, what I wouldn't want to see is if, like, you know, you're right here, and then I see the answer. Like, well, how did you get that there? I need to see who's putting minus putting it. To a point, yes. Like, you don't need to be, like, super specific, but I need to see the fundamental thing of calculus. Like, I need to see the v minus putting it, at least in some form. So that makes sense. Yeah. Okay. Yeah. Okay. Braden, what did you let u equal?
X squared plus one.
X squared plus 1, so then du is 2x dx. Okay? So no matter which method you went with, you would need 1/2 integral of u to the 1/2 du. Is that correct? Okay. If you change your limits of integration should be, what, 1 to 2? So we have 1/2 times u to the 3/2. Okay, so there would be like the exact version, right? Approximated, what was that? 0.609? Okay. I still need to see something along this lines. I need to be able to see that you use the fundamental theorem of calculus. You plugged in B minus you plugged in A. Okay, I know that your calculator can help you a little bit, but I still need to see the f of B minus f of A in your work, so I know that you are going through those motions correctly. All right, so in our last 10 minutes, I want to talk about something called average value. Okay, remind me, what are we finding when we take a definite integral? An area, okay? And we talk about area, so this would be the area under the curve. And when we talk about area, we're talking about, we typically like to think, well, 2 dimensions. Most basic, like length or width times height, okay? Or length times width, or whatever it is that you think of. But we're talking about 2 dimensions, okay? So when we find a definite integral, we're talking about a 2-dimensional calculation of area. Well, if I want to find the average value of a function, what we can do is we can use that area and divide out one of the dimensions. Okay? So what I'm going to do is I'm going to let you write it down first, and then I'll talk about what it means. Okay? So this is the average value of a function. And really, as long as you have like this part over here, okay, this is just the fundamental theorem of calculus on the right. Okay. So I'm going to rewrite this. Instead of multiplying by the fraction, I'm going to go ahead and make it all one fraction, where we have the integral in the numerator, and then b minus a would become our denominator. Okay, and I want us to think of it this way. So here, we would be calculating area, right? 2-dimensional area. Well, b minus a. What does b minus a give us? It gives us the length along the x-axis, right? How long is our interval horizontally? So if I take our 2-dimensional area and I divide out the x-axis length, then really we have 1 dimension length, right? Here we're talking about square units, and we divide by a unit. So we're left with just 1 linear unit of measurement. And we'd be talking about the y values, right? If we divide out the length of the x's, we're left with the y value. So we have that average y value of what our area would be using to calculate. Okay? So when we take area divided by our x measurement, we're left with the average y value of a function. So average value of a function, we're really referring to the y value. So on average, what's the height of our coordinates along an interval? That's what we're calculating. Okay? And it's as simple as taking a definite integral times a fraction. Okay? So let's try it. So we have the average value of this function on the interval 1 to 3. So our average value, we're going to take the definite integral from 1 to 3 of 3x squared minus 2x dx. That gives us our area, but we want average value. We only want a linear measurement, so we need to divide out that x length. So our interval, b minus a would be 2. Our interval is length 2, so we're going to have to throw the 1/2 out in front. Okay. And if you want step by step here, you want to write 3 minus 1 so you remember where that 2 came from. That might be helpful. Okay. Do we need U substitution for this definite integral? All we need is the power rule, right? So we have 1/2 times our power rule would give us x cubed minus x squared. So we have 1/2 times 3 cubed minus 3 squared minus 1/2 times 1 cubed minus 1 squared. Okay, what's 27 minus 9? Divided by 2? 9. So our average value is 9. 3x squared minus 2x. 3x squared minus 2x. Okay, so here is our curve. All right. Our interval 1 to 3, right? 1 to 3. Here's x equals 1. And then, okay, so x equals 3, we're going to have to like way up here. So the average y value from x is 1 to x is 3 is 9. Visually, does that make sense? Okay. We're increasing from 1 to 3 here at 1. Looks like 1, 1. At that 3, we're way up here. So on average, our height is 9. All right, I don't think I have time for my last example, which is okay. It was just another average value one. You have homework. It's coming from, I think it's 4.5. Does it have a letter next to it? No. Yep. So it's 4.5. It's right before the review and then quiz. Okay. So it's that 4.5 homework right before the review and then the quiz.